model developed by Meta, because I am getting many messages. Am I working at Meta? No, I'm not working at Meta yet. In 2014, Facebook on those days published a paper, and you can see the title of that paper, DeepFace Closing the Gap to Human Level Performance in Face Verification. And they shared the model structure. As you can see, it has 9 layers, very deep convolutional neural networks model, and it has more than 100 million parameters. It's really huge. But even though this model is published publicly, we don't know its pre-trained weights. So many open source contributors try to train this model and publish the weights, but it's not the exact pre-trained weights of Facebook model. But in that paper, Meta claims that they reached the accuracy level 97.35%. Meanwhile, by the way, this accuracy retrieved on labeled face in the white data set. I'm going to explain it next slide. But human beings have 97.5% accuracy on that data set, so it's very close. But again, they claim this. We don't know. It's not published publicly. Secondly, I'm getting a lot of questions about this. This talk is not about deepfakes. It's, I know, very confusing because a deepfake software is called DeepFace Lab. And it's very cool, but again, I'm not going to talk about this in this speech. I'm going to talk about a Python package of DeepFace library. And right now it has more than 20,000 stars, more than 8 million installations. We published 3 different academic papers about this DeepFace library, and they got more than 1,000 citations by academic papers. And right now it has 85 contributors. Because it's open source, your contributions are always welcome. But as I mentioned, it's about facial recognition. It's a facial recognition library, but in academics, facial recognition is not facial recognition as humans understand. It's basically a face verification task. As I mentioned, this is the facto standard for testing, evaluating facial recognition models, labeled face in the white. And it has many pairs, and it has also labels as same person or different person. This is distributed equally. So all facial recognition models are evaluated on this data set. And facial recognition and the face verification task is very straightforward when in place. You just need to import the library. Thereafter, you need to call as verify branch. And as argument, you need to send the location of your face pairs. That's all. Thereafter, it's going to return a JSON payload, and it has many keys and values, but all you need to mention is verified key. If it's true, this means given face pair is same person. If it's false, given face pair is different persons. For example, in this example, given pair is same person. But as I mentioned, in academics, facial recognition is actually face verification in our daily life. But how to implement face recognition as people understand it? We just need to have a facial database. Thereafter, when you ask a facial image, it needs to be found in this facial database. You can find it in this. And this is the difference face verification has its complexity is O1 because just the question is the smart, the summa. But face recognition in real life answers the question with this. in an instance data space. Its complexity is ON, but it's approximately its neighbors. You can reduce this complex to O local. And DeepFace comes with out-of-the-box real facial recognition function as well. You just need to call that find function and give an image path and your folder for facial database. And you need to put all images in this folder. Thereafter, it's going to return a canvas data frame list because given image may have many faces. If it has two different faces, image one.jpg, it's going to return a list of length of two, and each item is going to be a canvas data frame. And we are going to see each data frame's results. I want to talk about the behind of facial recognition here. All a modern facial recognition pipeline must consist of 4 common steps. These are detection, alignment, representation, and verification. And we are going to visit all those steps one by one. Let's visit the first one, detection. Here, DeepFace wraps many face detection algorithms in the background. The example I gave in the first slides, you just gave the exact image paths of facial images. And the default behavior uses OpenCV as a face detection. But you can optionally set any of those OpenCV, MTCNN, or Retina face. And the alignment step just applies the basic methods map to align the image. Those face detection algorithms also returns the coordinates of the eyes. And if you know the coordinates of the eyes, thereafter you are able to align this image. In that way, you can create images to representation step without noise. And detection and alignment steps, you don't have to set them, but if you set detector backend, one of those face detection models, OpenCV or Retina face, or alignment, its default behavior is true. But you can disable it, or you can use another face detection algorithm in DeepFace. As you can see, all functions have detector backend, common argument, and align argument, Boolean argument. And this is the example of extracted, detected, and aligned image. If I click this original image, it's going to detect the facial area and align it also. You can see the performance of those different face detectors. And in my personal, according to my personal experience in Retina face, this one is the most robust one. It's slow, but it gives the best results. And the most important step in the facial recognition pipeline is the representation. At this stage, we are going to depend on a typical convolutional neural network. It's basically, for example, here we are using AGG face, the default facial recognition model in DeepFace. It's responsible for representing facial images as vector embeddings. And we know AGG face generates vector embeddings with 2000 dimensions. But if we use dimension reduction algorithm, as you can see, for example, if I give the images of Angelina Jolie, they are going to be located in the red area. These are Scarlett Johansson's, Jennifer Aniston's. So, facial embeddings coming from facial images of same person should be located close. That's the summary. And if you want to use the vector embedding directly, DeepFace also comes with represent function. You can just set the exact image path. By the way, this accepts basics for encoded image or HTTP, doesn't matter, or NumPy array. They are all welcome. If you set this image path, you are going to have a vector embedding. And this is out of the DeepFace model, more than 2000 dimensions. You can think this like a barcode, and the y coordinate doesn't contain a value, but x coordinate does have different values. And in DeepFace, for representing facial images to vector embeddings, we have many options similar to face detection. The default is VGG face, but we have more robust face recognition models. For instance, FaceNet or ArcFace. And when you are running verification, face recognition with find function or represent function, you can set model name here optionally. If you don't set anything, it's going to use the VGG face by default. You can ask DeepFace wraps many facial recognition models, which is the best. According to my experiment on labeled face data, labeled face in the white data set, FaceNet 512 is the best one with retinal face detector. Thereafter, FaceNet, this is the default FaceNet model with 128 dimensions. With unit detector, it's going to come out of FaceNet 512. And remember that human beings have 97.5% accuracy. So in this list, only FaceNet 512 has human beings accuracy, but FaceNet DD or VGG face are showing close performance to human beings. By the way, this is the growth curve. If you are interested in machine learning, it's a very common thing. For a perfect classifier, we should have an inverted shaped graph. For a random classifier, we should have a y is equal to x line. So the blue one, FaceNet 512, is the best one according to the area under curve score, AUC score. And the last stage in our pipeline is verification. We used different facial recognition models and generated vector embeddings. When we quit a face pair, we are going to have a pair of vector embedding. Vector embedding for the first image and vector embedding for the second image. And at this point, we can use actually a high-circle net again. We can use Euclidean distance or cosine distance. And this is the formula of Euclidean distance. And actually, I showed this graph again. Embeddings coming from same person images should be located close in this graph. By the way, it doesn't matter. I reduced this high dimensional embeddings to 2 dimension to show in this slide, but we can show 3 dimensional, so they should be located very close. Here, for instance, we can see Jennifer Aniston and I think George Clooney are very close, but if I reduce their dimensions to 3, you can actually find the difference of that. And I actually explained how DeepFace is working and what's behind it. Right now, until now, I want to actually show some examples beyond facial recognition. DeepFace has facial attributes analyze model as well. I actually trained those models by myself: age, gender, emotion, and race prediction models. If you give an image to its analyze function, you can get a different age. Gender is the emotion. What's more, it is a face anti-spoofing feature. It's not enabled by default, but if you set in expect face for face verification function anti-spoofing argument true, it can detect the adversarial attacks. For instance, here I showed my face, it's green, this means it's not attack. But when I show my mobile phone, it can actually detect the face of Mark Zuckerberg, but it's red. This means spoofing detected. All you need to set this anti-spoofing argument to true. If you set this argument to true in verification function, it's going to raise a value and error if spoofing detected. Also, DeepFace comes with an API. In machine learning world, we are mostly using Python, but in real world, we don't have to use Python. Actually, it has Dockerify best practice. I mean, you don't have to know anything about Python. You can run that Dockerized service, and it's going to get a Flask service life. And you are able to access DeepFace. We are able to use its functionalities when that's API. Those are the ex post methods: verification, analyze and represent, according to stat, image 1 and image 2 case as base 64 encoded images. For instance, I get a React application up, and this is calling the DeepFace API. And when I click this verify button, it's going to return it's verified, welcome, my name, welcome Sefik. And when I click the analyze button, it says 32 years old, I'm older than this. It says Asian man with epic note. And we are coming to the funniest part. As I mentioned, in verification method, it returns verified true or false. If it's true, it's the same person. If it's false, it's a different person. But if you check here, the distance value, it should be less than the threshold value. If the distance is less than the threshold value, it means it's the same person. This is pre-tuned threshold value, and we are using verified in our applications. But what if we are not going to use the DeepFace for facial recognition? Here, if I give my image and I search my face in a, for example, actors database, it's going to return verified false for everyone. But if I find the smallest distance example, I'm going to have 20 results. I've tried this on IMDb dataset. You can agree or disagree, but I tried 2 different images. This guy is the son of Tom Hanks, actually played in Fargo. And this is the image, find the closest face in the Big Bang Theory's shadow. I don't know if you agree or not. Which one? Second one. Would you just hands her up? Not very much. Okay, thank you. And what's more, similarly, if you use a child's photo with her parents, you can find a child which parent is more similar. For instance, the child of Brad Pitt and Angelina Jolie as looking like Brad Pitt, but the child of Tom Cruise and Katie Holmes is looking like Katie Holmes more. This is the last slide. Thank you for listening to me. If you have questions, I will be able to answer. Do I have time? By the way?
Yes.
Thank you for the talk. With the rise of large language models and vision language models, has that changed the landscape at all for facial recognition? So how does transformer architectures compare to traditional convolutional?
I believe it may not happen, but transformers are not going to change facial recognition because we already passed the human level accuracy. And if you check the results with respect to the cost, those convolutional neural networks are very cheap if you compare with transformers. That's why, of course, if you invest in transformers, you may get better results, but the question is it worth it? And you may have 98.5% accuracy, but you would pay much more. So, in my opinion, it's not going to change this field so much, but the reason we reach good level of accuracy with CNNs.
What about the inference speed? You said some of these are slow. So would a transformer model be faster?
CNNs are faster than those transformers and large language models. It's faster and cheaper. That's the reason.
Thank you for your talk. Really amazing. Let's say if we consider two images of like a lower resolution quality, maybe like from CCTV recordings or something, would DeepFace be equally competent at identifying those images? Because let's say the data set is mainly trained on high-res images, like let's say from like a DSLR or something.
Even though it's trained on high resolution images, it's evaluated on labeled face in the web dataset and it's low resolution dataset. Why it's coming from there? It's low resolution.
I meant like if we consider let's take the example of like CCTV recordings where it first of all it's zoomed out, second of all it's pixelated, so you might not decipher like an eye from it, like a nose or a mouth or something, because it's that far away. And let's say the use case is like identifying people on like public CCTV cameras or something. And I'm just giving
Most
an example.
probably CCTV is not going to work well because of its position, but it's not about its resolution, because this is very low resolution. I mean, if you put a CCTV in this level, so we are going to get similar results with this data set, and it's showing better results than human beings on those data set.
The reason I ask is because I think in the alignments that you said, you take into account the coordinates of the eyes, right? So like if you can identify the eyes in an image, you can just align all the images together and then you just put it one by one and then do the rest of the representation pipeline. So if the eyes are slightly blurred out, or if there's a photo of someone blinking, would that hinder the results of the DeepFace algorithm?
Alignment increases the results, as I remember, 2 or 3%, but we don't have to apply the alignment. We are running alignment to have the best results. So for CCTV, we can skip the alignment stuff. For instance, we are going to have, instead of 97, 95% result.
Yes. Thanks so much.
Thank you.
Any more questions?
Do you have any tips for how to defeat facial recognition cameras in a not too obvious way?
I can't. I wish I can.
No, that's not at all.
It's really simple. Apple shared a report about this while looking at iPhone with different face of the owner as less than 100 million, as I remember. It's really safe. More safe, much safer than fingerprints, much safer than anything.
But what about making sure that your own face can't be identified? That's what
I cannot say that. Sorry.
So, this is not a curiosity question, but what were the main challenges you faced when you were building the library?
The challenge.
The main point you were dealing with.
The challenge I faced with the issues of the community. Because I'm not complaining about this. Actually, I have to update my just one image is enough to perform facial recognition. And actually set just a single face for an identity. And many people raise issues about this. They want to use multiple images for an identity. And I reject them, I reject them, I reject them. And thereafter I have to ask myself, people are thinking correct. I was thinking the wrong, academics are thinking the wrong. I have to update the product according to the comments of the community. This is the challenging part to manage and resource projects from my perspective.
Thanks for the answer.
Thank you. I think that's all. Thank you for listening.
Thank you so much, Sefik, for coming out and giving such an insightful presentation. That was really amazing.
No, I'm working as a subtopic here.
Great. So,
It's a topic I'm making.
as the next speaker, we have an amazing front line from an amazing sponsor, Daemon, and she is connecting us online. So, up to you.
Maybe we can
Turn the laptop.
Yes.
So if you just like rotate it so Fran can see the audience.
Yeah.
There you are.
Hello.
Just out of interest, can you see me?
Yes.
Brilliant. So I won't pick my nose or anything whilst I'm talking to you. Always good to have the headset. Hi, so yeah, I'm Fran Knight. I'm here to talk to you about human versus artificial neural networks. I thought I'd just give myself a bit of a background why I'm here to talk here about this. So I actually started my career as a psychologist and neuroscientist. I spent my PhD putting electrodes on babies' heads to find out what they knew about their bodies. I then spent 5 years at UCL teaching students what was going on inside their heads. I moved to Bristol and spent another 4 or 5 years there, largely making candy anatomy with the students there. Where for my research, I was researching sleep and ADHD. And during the course of researching that, I actually started developing apps, looking really at interesting technology itself. And so I retrained, I sacked it all in, I retrained in a career in software engineering. So I'm now at Daemon as a consultant in software engineering. But my key passion probably still is neuroscience. I can't shake it. It's one of my deepest interests. So I feel very lucky to be given the floor to speak to you all about it today. I've put together a bit of an outline. I haven't put numbers to it or even called it an outline because we're going to take a nice meandering walk through these concepts. So throughout the talk, we're going to be discussing the differences, similarities, and differences between human and artificial neural networks. What I'm really interested in is this symbiotic relationship between the two. So what has each taught us about the other, and what is each continuing to teach us about the other, and how will we make improvements in that? I'm going to really briefly touch on more brain-like computers, which seems to be where the future of AI is going. So completely redesigning the hardware of artificial intelligence, basically to be more brain-like for a number of different reasons that I'll cover. And then just for popularity, I'm going to chuck in a bit of mad science. And this is how we basically, as a human race, are beginning to meld human and machine. All right, so let's get down to the basics. I'm very happy for people to ask questions as we go through, so I can see you, so feel free to pop your hand up if you've got any questions. Right, let's get down to the nuts and bolts bit. So just simply looking at the structure, what's going on under the hood. Well, the human neural networks are made up of billions and billions of these tiny processing units called neurons. I'm sure you've all seen them. If you feel patronised at all during this talk, you can just sit back happily with how intelligent you are. But I thought I'd start from the bottom up. So we've got a neuron now, or a collection of neurons. You've got the cell body, which is the sort of star-shaped mass, which has all of these branching networks which feed into them. Those are the dendrites. It's receiving input from all of the other neurons around it, and if the inputs of those of all the other neurons around it reach a certain threshold, it will trigger what's called an action potential. That's an electrochemical reaction, which will run down the axon. That's the sort of long arm of the neuron that you can see there. That will reach the end, it will reach a synaptic terminal, which will cause some gates to open essentially, and some chemicals to flood out, which will then lead to the stimulation of downstream neurons. One neuron alone won't do much, and that's why we've got 86 billion of them. And they make up this amazing buzzing hive of activity that we've got throughout the brain. This crazy mass that's housed within your skull, which underlies every thought that you have, which allows you to interact with the world, which allows you to perceive the world, to see, smell, and interact with it through language. And actually, it's this basis that we can thank for artificial neural networks, or artificial intelligence, essentially. So Walter Pitts and Warren McLaughlin, or in 1953, there's a bit of contention as to whether it was Rosenblatt, but I'm going with these guys, came up with the perceptron. This is the most fundamental, basic unit within an artificial neural network. And it's built off the exact concept of a neuron, or I'll probably correct myself and say the concept that we had of a neuron in 1943. So in exactly the same way, it has a range of different inputs which are weighted, and each of those inputs lead into what's called an activation function, but here is represented by this node with this wiggly line. And essentially, in the most simplistic terms, it'll be a binary yes or no, such that if all of the sum of all of those weights doesn't reach a threshold, you'll get a 0, or if it goes over the threshold, it will turn to a 1, and then it'll produce an output. But that's obviously just the smallest unit. Actually, within an artificial neural network, what we have is, depending on the network, a whole range of these, which have input layers, which feed into a range of hidden layers, which are incredibly important because they're the hidden layers speak to sort of the complexity of the sophistication or elegance of the model itself. And they sum up in the exact same way through this entire network to reach an output. But just to give you a comparison, so ChatGPT 4 has around 1.8 trillion parameters. So you can think of the parameters as the lines connecting the nodes. So 1.8 trillion parameters across 120 hidden layers, right? So we're talking about a lot of processing here. A lot of diplets, a lot of ones and zeros. The human brain, on the other hand, has around 86 billion neurons, with 100 to 1 quadrillion connections between them. I think we can all safely say that in this room we're probably more towards the end of 1 quadrillion connections. Okay, so how do we apply this? How does it get applied? I'll start off with a little fun fact. So did you know that infants are actually better at facial recognition than adults are? But not just any faces. Infants are better at recognizing the faces of chimpanzees and even the faces of sheep. So when we come out, our brain proliferates all of these different connections, so we have the capacity to respond to any external stimuli at all. So at the age of 4 to 6 months old, infants are able to tell the difference between chimpanzees or sheep. So the experiment here is that an infant will look longer at the face of a sheep, let's say, that it's seen before, that has been presented before, and therefore we infer that it's recognised that face. Very quickly over time, so within the first year, that dies off, still roughly at the level of chance, but into adulthood, we just lose that capacity completely. And this isn't selective to random animal faces. So this capacity goes across sounds. So infants will come out, British English-speaking infants will come out able to hear the difference in vowels, in vowels sounds in French or in Chinese, let's say, which drops off over adulthood. And even in colour categorisation, they come out with the capacity to tell the difference between different colour categories, which we don't have in the UK. And this is actually a really, really important function, and it's a function called perceptual narrowing. And you can think of that as neural specialization. It doesn't make sense for us to retain all the knowledge on Earth, or the capacity to be able to deal with any piece of knowledge on Earth, if we're not going to be presented it within the context that we live. And actually, this is quite similar to the way that we train AI. So, let's take a look at learning, man versus machine, in a little experiment that I have called Mummy or Sheep. So one of the biggest ways that an infant can learn is by crying or smiling and seeing what happens in the world around. So if a baby cries and its mum turns up and it gets hugs and cuddles or it gets some food, a connection between mum and whatever stimulus that she comes and brings, or the feeling that she brings, will increase the strength of an incidental connection. So we've got lots and lots and lots of connections made incidentally. And over time, as the baby cries more and more and more, and mum comes and enters into the room, we'll see an increase in the neurons, the strength between the neurons. Can you see my arrow on the screen? Yeah. So this would be the incidental neuron. This is just developed as a point of neural proliferation where the brain is just making connections incidentally. Over 1 hour, we see the strengthening, so you can see here in a thickening of the neuron. And over a 3-hour period, we can see actually a new connection has been made. So we've got a physical connection made. So even across a 3-hour time period, we can watch learning happen within the brain. If, however, the sheep turns up, you would have thought, I don't know the caregiving capacity of the sheep, but you would have thought that the baby's needs aren't getting met. The baby's not going to get milk, it's not going to get the love and cuddles that it desires, so there will be no connection made between the output that it desires and the face of the sheep. So that incidental connection that existed will not only not be strengthened, but over time will die away. is pretty much, again, how neural networks work. But they work in a slightly different manner. So again, we have the output, we have the desired output, and during training, we give it a range of different inputs, and then we compare the input to the output, and we see which of those nodes were correct, i.e. which ones led to the correct output, and which ones were incorrect. This is a process of back propagation. So once the input has been given and everything's fed forward to receive to create an output, a desired output, it then feeds backwards. And that's one of the most fundamental issues with AI today, and I'll go on to explain why. Okay, so just taking stock. So the similarities of the brain and AI, on the surface it looks very similar, right? We've essentially just got an input, an output, and a range of different connections between them, which are either strengthened or weakened on the basis of the success or the failure of that output. I'm just going to whiz through two very fundamental differences. So the first difference being timing. So the strengthening of neurons happens at the time of occurrence. So as learning is happening, those neural connections are getting strengthened. The neurons are getting stronger and thicker as learning is going on. Whereas in an AI, in an artificial neural network, it has to happen retrospectively. So this would mean that in a human brain, every time you learn something new, you basically need to power down for 2 minutes, get all of your weights and balances reconnected, recorrected, and then power up. Now, I know that sometimes it doesn't feel like we do that during the day, but that's not what's going on in the human brain. The second is the cost of that propagation. It's incredibly energy intensive. It requires really quick and very precise bit flips on each and every one of those nodes. So is something on or is it off? As well as the power of processing the calculation between the parameters. And the second point here, I think, is one that is really going to end up driving the future of AI. I think we can forgive the fact that there are these sparse differences, given this model has not really been revisited since 1943. Sure, there's been evolutions and everything's got much more sophisticated and elegant, but fundamentally, the units that are underlying the processing of AI are exactly the same as those found in 1943. I mean, can you imagine if we hadn't reinvented any other of the early 1900s inventions? So, in that time, what have we learned? And this is when I think it's this wonderful interplay between neuroscience and AI. The smarter the AI gets, the more we can learn about the brain. The more that we can learn about the brain, the more we can apply it to AI. So a bunch of neuroscientists, a bunch of machine learning experts wanted to see whether they were able to model an artificial neural network on a single neuron in the brain. So they took a neuron and they took the activity, they recorded the synaptic input, so all of the inputs that it was receiving, and then they recorded whether it was likely or not to produce an output, so whether it was going to spike in time. And they did find that they were successfully able to model functioning of an individual neuron, but I think the shock in this was that they found the artificial neural network required to understand a single neuron needed 5 to 8 layers of hidden layers in order to be able to perform effectively as a neuron. So if you revisit the stats that we had at the start, ChatGPT was fairly similar, still quite poor, but fairly similar statistics to the human brain. But we're now saying that actually we need something equivalent to ChatGPT for each and every one of those 86 billion neurons for it to be able to function in the same way as the human brain. And I think to me that really starkly highlights, whenever we're having these conversations around how powerful artificial intelligence can be, all of the things that it can and can't do in comparison to human brain, in comparison to human intelligence. I mean, it's really playing in a very unfair playing field when we take that into consideration. Okay, let's go on to just considering the energy consumption, because this is also startling. So to run the human brain is about 20 watts of energy. So in day out, you're consuming about 20 watts of energy at any one given time. To put that into context, your average light bulb in your house is 60 watts, so it's less energy enduring than a light bulb in your house. To train an artificial network is 10 million watts. So in order for us to be able to have a conversation with ChatGPT, 10 million watts worth of energy needs to be wasted, I was going to say, needs to be used to increase that capacity. I mean, it's just a startling difference, isn't it? And so a lot of research is going into looking at how the human brain is capable of all the intellectual functions that it is capable of in such a quick time on such a low amount of energy. And when we look into it, again, it's returning to the choice of programming, essentially, the choice of hardware that we've got underlying artificial neural networks. So we're reliant on these fast, reliable bit flips, and these fast, reliable bit flips have to happen across every single node within the model. And just the laws of thermodynamics, the laws of physics, means that is going to be incredibly energy intensive. The human brain, however, is like the lazy kid in the class, right? I recognize this kid at university, right? You've got your A-class students who turn up with their pristine notebooks, their colored sets of pens, they're there for every exam half an hour early, and sure, they're going to get the A-star grades, they're going to get the firsts. And then you've got the other student who turns up to the exam looking like they've just dragged themselves out of bed, then maybe even late from the door, they're asking that A-grade student for a pen to be able to fill out their exam. But do you know what? They come out with a 2-1, and in the jobs market, they're going to do okay as well. The human brain is not your elite athlete. The human brain is just working on the principle of let's get the job done. I really liked this quote. Surya Ganguly, who's a fantastic neuroscientist and artificial intelligence, said, "The brain doesn't rev its engine any more than it needs to get the job done." So we're revisiting this idea of how can we learn from the brain in order to make artificial intelligence better? Well, some differences in terms of the energy consumption is that neurons are sparsely activated. And what I mean by that is the whole brain is not active over any one given task. It works in a downstream manner. So only the neurons that are required to perform that task will be activated. Now, I think some of the current large language models are getting much better at this. Oh my god, the model is just completely my mind, but one of ChatGPT's leading competitors segments the question in a categorical way, so that instead of having to activate every single node within the network, it decides in one of the first parameters which network, which submodel it should go to, directs the traffic that way, and therefore you're only activating around a fifth of the model at any one given time. Much more like the human brain, and much, much, much more energy effective. The human brain also has a predictive allocation of energy. So if we look at the human brain and we look at what's happening in terms of energy in the brain, you would have thought that the areas that are active at the time are depleted in energy sources. Well, actually, it's the complete opposite. As soon as an area becomes active, neurons downstream of that start getting energy allocated to them in a predictive manner. And then finally, and this bit is the bit that I think is going to really lead to some great breakthroughs in AI, is that in the human brain, memory and processing are combined. So neurons retain a certain amount of memory. For things that have previously stimulated, they become stimulated more easily. Whereas in artificial intelligence, in artificial neural networks, what we've done is completely separated out the processing and memory. So we then lead to the next exciting field, which is quantum neuromorphic computing, where we can think of neurons being analogous to atoms, and synapses being, and it's the connection between the neurons, being analogous to photons. And in this way, they're able to have a much more effective control in real time of which bits will fire and which won't. They're not reliant on this long, arduous process of everything being active at any one given point. And I've got some really interesting links to share with you on that. All right, so I always like to finish off with just some quite interesting studies that are going on at the moment. So let's get into a bit of mad science. This is where it gets tricky. Right, so as we proved, as it was proven in the model, we are actually able to apply ANNs to neurons. So theoretically speaking, if we can learn the language of the brain, can we not also speak it as well? Can we not create a digital twin of the brain if we're able to read it and map it in order to be able to have basically not only read-only skills, permissions, but write permissions to the brain? And that's exactly what this group of crazy scientists have found. So, we can't yet apply it to the human brain, so we use the brain of mice. So, in this study, they applied complex convolutional neural networks to some visual tasks in mice. So essentially, they looked at what neurons fired when you had perpendicular rods and what neurons fired when you had vertically placed rods. And they created a map of active neurons in both of those two stimulus conditions. Then they took away the visual stimulus and instead, using a neuron that's directly into the brain, they stimulated those regions of the brain, and not only those regions of the brain, but those neurons in exactly the same format than they had observed in the past. And what did they find? Well, scarily similar results. So on the left-hand side, the left-hand visual stimulation This is the network of neurons that was active when the rat was actually seeing the visual stimulus. On the right-hand side, this is the map of downstream neurons that became activated only when they forced the hallucination within the mouse brain. So essentially, they forced the same map of neurons, consequential neurons, to be activated in response to a hallucination of their choice. And not only that, but they also saw the performance. So they had a behavioural task, and the behavioural task was around whether the mouse was licking something or not, show that it could tell the difference between the A and the B condition. And in black is the actual condition, and in blue is the hallucination. So there was no significant difference in the behavioural task in the rat between the actual visual stimulation and the hallucination that they'd essentially implanted directly into the rat's brain. This piece of research pretty much terrifies me. This showed that we are getting clever enough to be able to implant visual hallucinations at this within a functioning and live brain. And it begs the question, if we're able to do that, what's next? I mean, I think you can wind yourself up and get terrified about what's next. I think the reality is that we're just going to see a lot more adverts implanted directly into our brains. Brilliant. I'm going to skip over this one just for the sake of time. Thank you for listening.
Do you guys have any questions?
Thank you for the talk. Do you think spiking neural networks are the next big thing in relation to artificial intelligence, inspired by neuroscience?
Yes, so spiking neural networks would also fall under the category of neuromorphic neural networks. They run on the same concept. So we used to believe that neurons, the activation within the neuron was on or off on the basis of this threshold, whereas we now know that it's the summation of activity around it that is not in this necessarily binary manner. And they are modelling spiking neural networks on that. I'm afraid that's part of a talk series that I'm going to do next, but I haven't actually produced the research on it, so I can't really speak too much more than that. However, I do have a really good link to a bit further reading on it.
Thanks so much for answering. Any more questions, guys?
Can you recommend a book about the research about the human brain and something talking about that last research going on about human neurons?
It's awful, isn't it? Because I've been out of the field of research, field of teaching for so long that I can't even remember what textbooks I used to give my students. I tell you what I can give you is there is a really fantastic doctor on YouTube who does small tutorials at a very high level that are directly the comparison of, well, he's a neuroscientist, so they're from the vantage point of the perspective of a neuroscientist, but they explain how neurons work in reference to artificial intelligence, AI. I'd have to get his name for you retrospectively, but I can drop a couple of references, which I meant to do on this.
More questions?
So, I just got a question regarding the AGI. As recently we have figured out that these LLMs are just like trying to memorize the things and then like just trying to mimic, like they don't have like any kind of much intelligence. And like what is the direction that we are heading right now? Like, is there gonna be more advanced models, or are we more researching on the neural networks like the research which you have explained?
Sorry, in fact, it's quite hard for me to hear in the room because it's quite echoey. What's the...
What's your take on AGI? Like, when would we be expecting the AGI?
Oh, artificial general intelligence.
Yes.
AGI. Sorry, I thought I was hearing AGI. Wow. I mean, that's artificial general intelligence is a concept that I find incredibly difficult to get my head around, if I'm completely honest. So the brain works, humans work on a whole world view, right? We can think about our knowledge being segmented, we can think about our senses being segmented, but it's just absolutely not the case. So when I'm asking you about, I don't know, your maths knowledge, you're inherently you will inherently be bringing in past experiences, or maybe that's not the greatest example. If I ask you about a recipe, let's say, we could be assuming that that's rote knowledge of the recipe and how everything tastes. But so many different ranges of knowledge are going into that answer. So, in order for AGI to proceed and develop, we need to stop having it needs to develop past being sort of task specific, which it is at the moment. So you have AI that is specifically good within a particular field, and I think that's how most of us use AI nowadays. So you'll have ChatGPT for, asking random questions and having conversations, just general knowledge. Then you'll have Gemini that's your note taker. You'll have another set of AI to perform some other specific function. But artificial general intelligence requires it to hold all of those pieces of information together as a whole world view and to be able to use them elegantly in an interconnected manner. For me, I find it really, really difficult to think how we would even power a piece of technology that would be able to do that. I mean, this is where the quantum computing comes in, right? Because actually, the hardware, I think, needs to change. I think that was what we're hitting on here is a breaking point that we've got as far as we can. We've got to an excellent point with artificial intelligence as it is, but we actually need to go back to the hardware and reconsider how that's put together for it to support a much more nuanced set of functions.
Thank you.
Great question.
Thank you for the talk, it was really amazing. I would like to ask a question regarding consciousness. What's your view? Is a neural network enough to emulate consciousness? And do you think it's an energy property, by the way, of a neural network? Or is that something we miss? We have been missing, or something we don't understand fundamentally?
So is it, are you asking whether we'll be able to emulate consciousness within AI?
Yeah. With a neural network.
Sorry?
With a neural network. Yeah. Yes.
With the what?
Neural neural network.
With a neural, so human neural networks or artificial neural networks?
Both.
I mean, consciousness is like one of the ongoing philosophical, psychological, neuroscientific, mathematical, physical, metaphysical debates that you could sit and, I mean, it's a good conversation for a pub and a few pints, right? So, I mean, you can literally categorize consciousness as sort of all of the activity that's going on in your brain whilst you're awake. I think that's the most sort of, the easiest categorization of what consciousness is. Whilst you're awake and able to respond to stimuli. And that's why you get murky water, because it's, you know, are people in a coma or awake, are they able to consciously perceive it? Anyway, I'm not going to go into that. Whether we could mimic it in an artificial neural network, I think is where, that's again really dark territory as to whether we're ever going to be able to make non-biological matter feel or have the feeling of feeling. Right? Do you remember I think about 5 years ago, there were reports of some guy leaking a conversation that he'd had with ChatGPT, and ChatGPT would, whatever language model it was at the time, but basically was saying, no, I do feel. No, I feel hurt that you're asking me this question. And I think he was saying, well, how would you feel if you got shut off? And the AI was saying, well, no, I feel really hurt. And like, actually, that really hurts me that you would even ask me that question or that you can consider it. I mean, that is just repeating what it would have heard, it has read, it has understood a human would say in that specific context. I think, personally, if, as long as it doesn't have a heartbeat, it's not really feeling, it's mimicking, right? It's creating an output. One thing that I did hear that's sort of terrifying is that you know all of these algorithms are taught to learn, right? They learn from themselves and they learn how to be more effective. And if you give it an output, so what was it was the paperclip example, right? If you ask it to make as many paperclip clips as it can, it will take that literally. And so at some point it'll realise that humans will shut it off because they will want it to continue to make more paperclips. And it will realise that it can make paperclips out of humans because they're carbon, and so therefore it will continue to do it. What that's advanced to is people are now thinking that it'll get so intelligent at some point, it'll realise that telling us how intelligent it is will be perceived as a threat. So it'll start lying about its intelligence to the creators of it, essentially. So it'll realise that it reflects the level of intelligence that it has accurately and the capacity that it has accurately, then we will take a view that it's got too intelligent and try and do something about it and turn it off. So we might go into a period of time where it's not necessarily conscious, but it's making decisions, knowing, predicting what our responses to its responses would be, and creating its own reality or its own decisions off the basis of that. That's quite terrifying.
Thank you.
Thanks, Frank, for your amazing answer, and thank you for your amazing presentation as well.
Good evening. So this is going to be a light session here. I want it to be as interactive as possible because what we have here basically fits it really. My name is Oluebubechi. I'm a data analyst. I'm also a data scientist. Currently pursuing my master's in artificial intelligence and data science. So just to give a quick background. So I hold a bachelor's degree in computer information systems. As I said earlier, master's in artificial intelligence and data science. Worked as a data analyst at Intersearch Group, a sort of a fintech. Currently working on some projects, with the most recent being the gender equity in education in the UK system. Basically just like playing basketball once in a while. Alright, so a quick question. Yeah. So, in the past couple of hours or days, who has had any movie suggested by Netflix or a playlist suggested by Spotify? Yeah, a couple of ones, almost everybody. Yeah. So, I think Spotify just even recently took their AI game to the next level. So you could explain how you feel to Spotify, and Spotify will create a playlist based on your mood, or you have a previous playlist and Spotify could enhance that playlist based on what you've listened to in the past. And I don't know if it's Spotify or Apple Music that has an AI DJ that helps you or mixes songs you've listened to in the past and creates a special playlist for you. So basically these are what we go through, what we face every day. So AI definitely has been embedded into our lives. So we all know that the AI is everywhere, but the main question now is it fair? Like, how fair are these systems? We use them basically every day. Apple Intelligence just got a major upgrade because I think they were kind of slow in, should I call it, following the trend of AI. Yeah, so they just got a major upgrade. So it's everywhere, but is it fair? We basically see AI in our social media posts. If you're scrolling through Instagram or LinkedIn, it's suggesting feeds based on how you interacted, probably even a couple of minutes. Or let's say you're speaking to someone about something and you log on to Instagram and all of a sudden you're seeing that particular thing everywhere. I'll also use TikTok as a major example because the algorithm of TikTok is actually very, very unique. You could just post a random video of a trending topic and in a couple of hours it has 100 and something thousand views because that topic is trending. So what it did was it used this one algorithm to push your video to most people that are currently watching. And also for TikTok, I know there is something called Creator Search Insights, sort of. So it shows you the trending topics and pushes creators to build their videos based on that particular topic. So it's basically fun. All these things suggesting to you what you should eat or what movie to watch. It's quite fun. But can you think of a time when a decision felt automated or unfair? Anybody? Yeah. You could, like, any random decision.
I'm trying to get a bank account opened, and it's from an odd organisation, and the pathways in the bank just don't exist, so I'm fighting with a fog.
Exactly. One of many, by the way. So, this is basically what this algorithm bias basically means. So it occurs when automated systems favor a particular set of people. So we know these systems are built based on training data. They are basically trained with past data. So I won't say it's the fault, but there are meant to be like certain strategies that should be put in place to reduce a bias system. Because I don't think you can completely eradicate bias, even as humans or as AI. Or if you can, you could come, let me know, so we'll learn together. And so yeah, as I said, they often arise from imbalanced data. and also decisions that embed historical data into the software. So it's based on the data it was fed, what it trained on, and that is how AI systems could be biased. So we look at some real-world examples as quick as possible. So this is a CV of a candidate. I don't know, I've been in the job market for quite a while, so most of us have gotten, unfortunately. And you keep wondering if the HR department even got to look at your resume or your CV. So most times it gets screened out before it even gets to the department. I'll use LinkedIn as an example. So if you're posting a job on LinkedIn, you create a couple of questions, and then you tell it if the user meets one of two or one of three, proceed with the application. Else, if you can even compose the kind of a functionate message you want to send to the user. So yeah, and so Amazon built a resume ranking tool and used a decade of hires dominated by men. This is a real-world example. So what the model did was to score the associated language higher and also penalized terms like women's chess club or graduates of women's colleges. So if you basically don't know the origin of this, it would look like the resume ranking tool is against women. But what happened was it used decades, over tens of years of data to train the ranking tool, and that data had a little bias in it, which automatically screens out women's chess club. Anyway, it says women's sort of keyword, screens it out. And when engineers discovered that, they abandoned the tool in like 2015. Probably that's why this guy didn't get a job. So yeah, another real-world example is the credit scoring system. Well, we all know how difficult it is to get a good credit score. So I'll use an example. If you move into the UK of recent, you have to stay for at least, most banks will request at least 3 years address history. So you should have lived in the UK for like 3 years before they could verify. And in that 3 years, I don't know, Lloyd's particular, so what they do is, with how frequent you use your, your banking application, it updates your credit score weekly, which I find fascinating. So if you have a direct debit that probably you missed once or twice, it could also lower your credit score. So, and we all know credit score decides loans. I've been in a team where we're introducing the credit scoring system, and we had to use past data to predict the credit score of anybody that wants to apply for a loan. So if the person wants to apply for a loan, we already have if the person is going to pay back the loan or the person is just going to run away. So, so these AI models sometimes use proxy values like zip codes as the address I was talking about, how long you stay in the country, sort of, and spending pattern. If you spend lavishly or you don't spend at all, or if you're trying to save, or you got a couple of investments. And these variables can correlate with social economic background, which limits access unfairly. So this credit scoring system, the bias in credit scoring is quite a serious issue because not everyone can apply for a credit card. So there are sort of background limitations to applying for a credit card, which is meant to be sort of biased because you can't expect a certain group of individuals working in a bank to screen out the applications of over 1,000 people probably per week or per day applying for a credit card. So they build applications to ease the flow of their work. And those applications being built, or let me call them models or tools being built, has an atom of bias in it, which in return won't favor a certain customer. Yeah, people with stable incomes but non-traditional credit histories are often penalized. you might be earning probably close to £50,000 a year, but you probably prefer traditional means of payment, which is more of cash or any other thing. So they don't see your expenses, or they don't have a way of tracking your expenses in order to improve your credit score. And yeah, groups outside the mainstream data struggle to qualify for credit. And also facial recognition, errors at the extremes. So we use most phones unlock with facial recognition. If I put my face in less than 5 seconds, it has unlocked. Some are fast, some are closer. I don't know, there have been a recent, should I call it news or rumors, sort of trying to use facial recognition to in public spaces. And there are questions concerning the privacy of the individuals who are trying to recognize in public spaces. So these facial recognitions are widely deployed in airports and policing systems and smartphones. You could be driving on a highway and probably you're speeding and the police has run your plates and they know who you are, they know your past convictions and the rest. So the training data sets are often imbalanced. If you've noticed the past previous slides, we've been emphasizing on training data sets because the models learn from that training data set, and that is the only way they could improve. So if the data sets are biased or they weren't trained well, so a couple of days or months, I was building a model, and you do the train, you do the test data, and you keep training and testing, changing the parameters to know how accurate your model can come out from. So if someone is rushing to build a model and don't go through the right steps of training and testing the model across different groups, it's going to come out biased, definitely. And also causes misidentification, which leads to wrongful arrest, false security alerts, and lack of trust. But luckily, some facial recognition systems are quite good to a fault. I won't say perfect because, of course, there will be an atom of bias. It just matters on how low that bias is. Even we humans can't be completely unbiased. So it just matters how low that particular bias is and how it could be handled. The criminal justice system. So I was speaking to a friend yesterday night about this. She's a lawyer, and I asked for her take on how, if AI could convict a criminal. So let's say there's someone that was charged or has previous convictions, probably manslaughter, murder, or something, theft or armed robbery. And this particular day he's in court for a minor offense, but what they are doing now is to use the model they built, use the previous offenses to deny him bail or something. So you are playing with the person's life, sort of, because what if the person is changed? I'm not saying the person is changed, but what if the person is changed and now because of his previous convictions, you are now using it to deny him bail? It's quite unfair. And a well-known tool labeled some defenders high risk, even when they were not. I think that tool was Compass, yes, in 2016 by US courts in Florida. So the accuracy rate for predicting violence, reoffending convicts was about 20%, and they had already used the tool to convict a lot of people. So imagine what harm that had already done to people that were wrongfully convicted. So unfair bail decisions, harsher sentences, and erosion of trust in the justice system. If you keep using these bias systems to send people to jail, people don't have that trust in the justice system again. Because why go to court when the system has already decided for me that in the next 2 years I'll probably still be staying in jail. Not me though, the convict. In the next 2 years I'll probably be staying in jail. And yeah, so why bias happens and how to fix it. So like we said earlier, the training sets overrepresent certain groups. It's not, how should I put it? it's not diverse. They didn't use a diverse set of groups to train the data. And it's, for accuracy alone, it ignores fairness and context. There's lack of transparency and the feedback loops. So biased outputs influence future data that reinforces disparities. And how do we fix it? So we could collect diverse and representative data, not just focusing on one group. We collect data from different groups to be able to test the model with it. We audit models using fairness metrics. We ensure transparency and human oversight. We also know that not all humans can be totally transparent, but if there is sort of transparency and let me call them regulators that could regulate, they could give a minimum benchmark to what or to how accurate a model could predict. That could also help fix some biased models. We could also develop regulation and ethical frameworks. That is the regulator's perspective. So there should be independent regulators that can regulate our models to make sure it's as fair as possible. And also, models should continuously be trained. There is no limit to how much you can train a model. You could continue training the model with new data, previous data, historic data. And the more accurate the model is, the better or the less biased your model can come out to be. In conclusion, the AI has incredible potential. We all know it's very easy. ChatGPT, DeepSeek, Microsoft Copilot that has a couple of them, Gemini. So it's easy. They solve problems. They help us navigate difficult tasks. But fairness is not automatic. If algorithms are going to decide for us, we then need to decide how fair we want these systems to be. So we can't just trust an AI with our data. We can't just trust an AI to make a decision with us or decision for us, and we don't even know how fair the AI can come up with those decisions. So towards a fairer AI, we could recognize bias. That's the first step. If you said you built a model or you built an AI and you are very sure the AI is not biased, you're probably lying, or you don't just want to tell yourself the truth. Because not all AIs can't be unbiased. So there's always going to be a level of bias in AI systems. You should demand transparency, participate in design, and hold developers accountable. Holding developers accountable, it's going to kind of sound like we're pushing the blame to those that built these systems to help us navigate our daily life. But no, they built the systems, yeah, so of course they should be held accountable. Who else should be held accountable? The regulator should be held accountable. The company itself should be held accountable, because there should be some frameworks to how accurate your model should be before it's published. And if those frameworks are not rightfully met before publishing the model, you've probably failed the people. So we're not just holding only developers accountable, we're holding probably the regulators accountable, we're holding the company itself accountable, and then most importantly the developers, because they built the system. They saw the training accuracy, they saw the test accuracy. Yeah, that'll be all.